Students, and in this lecture we're gonna talk about a compound microscope, right? So here you've seen that I've just drawn the ray diagram over here, and we can see the actual diagram of a compound microscope in your books. All right, so first we got to know that what exactly is a compound microscope and why do we need it. Okay, so if we want magnification much more than that of a simple, you can say, a magnifying glass, what are we going to do? We're going to use a compound microscope. A compound microscope uses two kind of lenses to produce magnification, which uses the magnification effect or the angular magnification of both the lenses. All right, so it's actually the combined effects of two kind of lenses here. Okay, so here is a microscope, a compound microscope, and here in front of us we have an eyepiece lens, an objective lens, and an object. All right, so here we have placed an object over here. Okay, here is our objective lens, which is just a convex lens. Okay, and an eyepiece, which is another convex lens. Okay, so how does it work? What calculation are you needed to just calculate the image formation or the magnification, you can say, for the compound microscope? Now we're gonna just now look at the ray diagram for it, right? So here I have drawn, you can see, two lenses over here. One is a smaller one and the other is a larger one, and the object is placed at the left of this lens, the convex lens. The condition for the magnification is that the distance of object from the lens should be very close to the focal length. Okay, so the focus point and the object should be very close to each other, such that the the DO should be almost equal to F. Okay, we have to place the object such that the distance of the object from the lens is almost equal to the focal length. Okay, now here we have denoted the focal length with FO, so we are gonna write here FO, of course. Okay, so this is the condition that we need to follow, that need to be fulfilled in order to get the right equation for the compound microscope, right? So to make the image by using these two lenses, we have to draw the ray diagrams, of course. So here is our object, and we have to draw three kinds of diagram as we've already been always be drawing on. This is the array, okay, which strikes the lens and gets refracted back through the focus at a certain point and beyond. The array, which passes through the center and travels till it meets the array, and it further travels just beyond that ray, right? And the array, which just first passes through the focus, strikes the lens and gets parallel to the principal axis, intersects these two rays, and of course travels beyond that. Okay, so the point where all these three rays intersect each other is the point where the image would be formed, right? So you can see here that here the object was not so was a small one, but here the image was magnified, but it is not as much magnified as we want, right? We don't need just a little magnification over here. Okay, we need a way greater magnification than this. All right, so for this, what are we gonna do? We're gonna introduce another lens, another convex lens, and this lens is here. Here is called the eyepiece lens. All right, this is called the objective lens, and it is called the eyepiece lens. All right, eyepiece because the eye is gonna see through it. All right, okay, so after just striking this lens, okay, these rays are gonna get refracted. But if we just draw these lines back, okay, it doesn't mean that it will strike this lens and get reflected back. They won't get reflected. They will come to this point, and after that it get refracted. Okay, here what have we done is that we have redrawn these rays so that they meet at a point where the second image would be formed. All right, so you can see here, by using two kinds of lenses and one object, we have obtained two images at the same time. One image at here due to this length, and one image at right over here due to the eyepiece, right? And you can see now that this image is much more magnified than the actual object, right? And it is inverted in direction, so it would have a negative sign with the magnification. Okay, and it is virtual image. Why it's a virtual image? Because it's on the same side of, as that of the object, which in the case of lens causes a virtual image to be formed, right? So these were the focal lengths of the lenses. FO is the focal length of this lens, and FE is the focal length of this one, the eyepiece. Now, what are we gonna do? We are gonna use these terms. Okay, we're not gonna use tan theta over here. We're just gonna use the magnification formulas over here. Okay, so we're gonna use two types of magnification formulas. We have read about two types of magnification: the original magnification, which happens due to the lens, and the angular magnification, which we have just studied in our previous topics. The angular magnification, which happens due to the position of the eye, right? And it depends upon how much farther or how much nearer the eye is, and how much nearer or how much farther the image is formed, right? So first we are gonna just calculate the magnification made by the objective lens, right? So magnification by objective lens is the simple magnification that we've already studied in the lens formula, which is MO equals to HI divided by HO equals to DI divided by DO. We're not going to look at this part yet, okay? So this is the magnification formula. Okay, we have introduced a negative sign over here because the image is inverted. All right, if it was not inverted, then we would have just kept it positive. Right, we have introduced it because the image is inverted, so there would be a minus sign over here. Now DI over DO. In the start of this lecture, I had already told you that DO is approximately equal to FO. Okay, because the distance of the object is approximately equal to the focal length of the lens. So what are we gonna do? We are just gonna write FO. Okay, I have wrote the wrong thing here. This is FO. Okay, DI over FO. This becomes our first equation. For the second equation, for angular magnification of the eyepiece, we're gonna write ME equals to N by FE, which is the angular magnification formula, which we have studied in our last topic, angular magnification. All right, we're going to use this formula and not the one with +1 added to it, because right here, the image is not formed just closer to the eyepiece. It is formed much farther from the eyepiece. All right, as it is at almost infinite distance, we can say it is much farther than the eyepiece. So we are going to use the formula for the infinite distance of the image, right? So this one was the image formed right here for this lens, and this magnification is for the image formed by right here by this lens. All right, so as the total magnification is the combined effect of both these lenses, the magnification produced by both these lenses, so we are going to multiply both the magnifications. Okay, So the resultant magnification would become the magnification by the objective multiplied by magnification made by um, the eyepiece. All right. So MO multiplied by ME. We've already calculated their values, DI over FO for capital MO and N by FE for small me. E stands for eyepiece, O stands for objective. This is the final equation that we need to just calculate the magnification of a compound microscope. It depends upon the distance of image, the distance of like the focal length, right? The N, no, the distance would be focal, the focal length, right? Here is the focal length, of course, into N, which is of course the near point. All right, what do we have here? We have the near point of the eye. N is the near point, which is approximately equal to 25 centimeters, and FE, which is the focal length of the eyepiece. All right, DI, distance of the image, F is the focal length of the objective lens, N is the near point of the eye, and FE is the focal length of the eyepiece. All right, so this is what we needed to just evaluate for today. Thank you so much, everyone.